Welcome everybody to lesson 9 of our friendly introduction to abstract algebra. Although we still haven't developed any real theory yet, we have met some interesting examples of finite groups. For example, the integers modulo n. These showed us that there is actually to every natural number a group of this order, but abelian in this case. Then we studied the symmetric groups of order n factorial. Those were non-abelian groups for n greater than or equal to 3. And in today's lesson we are going to take a closer look at the dihedral groups, d sub n. We already did this, in particular if you did the exercise on problem set number 3, I think, 2 or 3. But there you need to have a strong background in linear algebra or knowledge about matrices. Today we are looking at those as subgroups of the symmetric groups. And for this you do not need any knowledge of linear algebra or matrices, and we will arrive at the same results that we had back then. Okay, before we look into the details, this is what we are going to prove. Proposition 12, we will exhibit two permutations in Sn that generate a non-abelian group for n greater than or equal to 3 with two n elements. And this group corresponds to the symmetry group of a regular n-gon. This is our goal to prove in this video, or maybe 2 videos, let's see. Okay, to achieve this goal we need the following prerequisite on generators, or the group generated by a set. As always, G is a group. We take a non-empty subset M, not a subgroup, this is important, arbitrary subset, and then we define the subgroup generated by this set in this notation, in these pointy brackets, as the smallest subgroup of this group G containing this set. This means the following: if I have any subgroup of G that contains this set of elements, then this here must already lie in H, so be a subset or even a subgroup of H, because M brackets is also a subgroup. This means being the smallest. Exactly this condition here. And the elements of M then are called the generators of this subgroup here. Now, does this subgroup always exist? The answer is yes. This is a rather abstract definition and is not useful at all for practical purposes or if you want to really work with this subgroup generated by a set, but it shows that clearly this here exists. What do? We take the following set, we take all the subgroups of G that contain this set M. This here is clearly a non-empty set. Why? Because G itself is a subgroup of G that clearly contains M by assumption. So this is a non-empty set. Now we take all the subgroups that lie in here, could only be G in an extreme case, but we take all the subgroups and then we intersect them. Now, some problem sets back, we thought about the fact that the intersection of two subgroups, or actually any number of subgroups, is trivially a subgroup again. So this here is a subgroup. Is it the smallest? Why, yes, because we intersect all the subgroups that contain M. So this must be the smallest subgroup containing the set M. All right, if you didn't fully understand that, do not worry. As I said, this is not useful and therefore not that important. But proposition 11 contains a much more useful description of this generated subgroup. So the assumptions are as above, M being a non-empty set of a group G. Then the claim is that this here, the smallest subgroup containing the set M, looks as follows. We take all the products of elements in M, finite products, because we do not know what an infinite product would be, And this need not be a finite set, M. All right, we do not need to be in a finite group, so M could also be an infinite set, but still we take all the finite products, n can be any natural numbers, so I can take the product up to x sub 1 million or whatever, of all the elements of M, and this exponent here is either 1 or minus 1 for all the indices I. That looks a bit troublesome at first, but it is really not, because when we think about the subgroup criterion, what do we need for a set to be a subgroup? Well, it must be closed under group operation. I call it multiplication here. So if x1 is in this set and x2 is in this set, then clearly x1 composed with x2 or multiplied by x2 must also be in this set. And this is what we do here. We take all the products to guarantee that the products lie in this set here. Okay? For example, if M is x1, x2, then x1, x2 need not be an element of M. Yeah? Except for the trivial case when one of those is the identity. This need not be an element, so already this product would fall out of M, so this here has no chance of being a subgroup. So we collect all the products and put them in this set here. Now what else do we need for a subgroup? We need the subgroup to contain the inverses. So if x1 is an element of M, then its inverse must also be an element of the subgroup containing M. And as before, this need not be the case. If M simply is a set, then the inverse of x1 need not be an element of M. So what do? We also take all the inverses. For example, in this product here, we take the inverse of x1 and then all the finite products with all the other. And then the finite products with all the other elements. So the idea behind this should now have become pretty clear. Simply take everything you need, all the products, all the inverses, and write them down as those so-called words. Then you get a subgroup. And because I simply take everything I need and not more, this will also be the smallest subgroup. This, of course, was no proof, but I hope it motivated the idea behind this set here. And the proof is actually left as an exercise for you. Now, in general, this is pretty mean, but as always, there will be an instruction on the problem set how to do that. And if you fail, there will be the solution video where I explain everything in detail. Now, what we actually want to do in this lesson is to construct Dn as a subgroup of Sn. And if you remember the beginning of the series, we already did this for n equals 3. There we very concretely described symmetries of the equilateral triangle as permutations. And nothing else is happening here, but now for general n. All right. So let's take a look at two examples. Here's the regular pentagon. It's not perfectly, but I hope good enough. And here the regular hexagon. Now I'm going to describe two permutations to you that will turn out to be the generators of this group here, the group of symmetries. So R, as before, is the rotation by 360 degrees divided by the number of vertices. So in this case, 72 degrees. What happens if I rotate this pentagon around its center by 72 degrees? Well, 1 moves to 2, 2 moves to 3, 3 to 4, 4 to 5, and 5 to 1. And this is exactly what this 5 cycle here does. Remember the cycle notation from the last lesson? This 5 cycle here clearly corresponds to the rotation by 72 degrees. Now we also need a reflection to get all the symmetries. Here we take the edge between vertex 1 and the last vertex, vertex 5. And here, And now it's generally true that the line going through the middle of this edge, and that is perpendicular to the edge, is always a symmetry line of the regular n-gon. Look at that. If we reflect about this axis, clearly you get the same pentagon with different labelings. We have a symmetry. And also here, I take the edge between 1 and 6. Here the line going perpendicular through the middle. And again, reflecting about this line gives me a symmetry of the hexagon. Now, the permutation representation is as follows. 1 goes to 5, 2 goes to 4, 3 stays where it is, and 4 goes to 2 and 5 goes to 1. Now we take a look at the cycle decomposition. 1 goes to 5, 5 goes to 1, so we have our first transposition here. 2 goes to 4, 4 goes to 2, so we have the second transposition here, and the 3 stays fixed where it is, so we do not write the one cycle 3. And this here clearly is a permutation of order 2, because if I square that, if I compose it with itself, I end up with the identity. Same here, the 6 cycle 1, 2, 3, 4 and so on. 5 and 6 is the rotation by 60 degrees, and the reflection about this axis looks like that. And you see, you simply write down the numbers in the reversed order down here. And in this case I get 3 transpositions. 1 goes to 6, 6 to 1, so I have 1, 6, and similarly 2, 5 and 3, 4. And again, this is of order 2 because I have disjoint transpositions. If I square all of them, I end up with the identity. And now this is easy to generalize to arbitrary n. And well, I'd say we always take n greater than or equal to 3 because d2 is really not interesting. It's just the symmetries of this line here with 2 vertices. This is simply a group with 2 elements, abelian and not interesting. So this n cycle here corresponds to the rotation by 360 degrees divided by n. This clearly has order n, as we showed in general on the last problem set. And the reflection looks like that. As I said before, you simply write down the numbers in the reversed order. And this here can be decomposed into transpositions. And it turns out that this always has order 2. You can also see that in this representation here. Simply, that's a good exercise, square this, compose it with itself, and you end up with the identity. Because, for example, 1 goes to n, n goes to 1, so 1 goes to 1 if I apply this here twice. And in general, this might be useful for the exercises. S applied to any number I between 1 and n is simply n plus 1 minus I. Let's test that. S applied to 1 is n plus 1 minus 1, so n. Alright. S applied to n is n plus 1 minus n, 1. Okay, and all the numbers in between similarly. So those two guys here will be the generators of the dihedral group Dn, as we will see now. Alright, now we come to a very important relation between the generators, the so-called commutation relation, because it says that let's always assume that n is greater than or equal to 3, because for n equals 2, R inverse is actually R, and they do commute. So when I take S composed with R, it is not the same as R composed with S, because for these n, R inverse and R are not the same permutation or symmetry. So if I want to commute, I have to put the inverse here in front. And this can be generalized to this commutation relation. S composed with the kth power of R is the same as the inverse of the kth power, or R to the minus k, composed with S for every those k. Of course also for k equals 0, but then it just says S equals S. Exercise, very important to do that on your own on the next problem set. And from this, as I said, it follows that this Dn is a non-commutative group. Oops, we haven't defined Dn yet, but when we have defined Dn, we will see that it is non-commutative because those two do not commute, S and R. All right, now for the definition of Dn as a subgroup as Sn, we take the two generators, hence the name. So the set consisting of R and S, this clearly is a subset of Sn, and then we take the subgroup defined by those two as defined before, and here to shorten notation we leave away these set brackets and simply write it like that inside the pointy brackets here. Now by proposition 11, the group generated, the subgroup generated by those can be written as those so-called words in R and S. Actually, there's a little bit missing, but again, you do the details on the next problem set. So those are the words. And now using this here, all those words of any length can be collapsed to those expressions here, R to the K, S to the L, where K runs through these numbers and L is simply 0 or 1, because S squared already is the identity again. As I've said, you do the details on the problem set. And this here can be written like that. If X is the cyclic subgroup generated by R, containing all the powers R to the K, and Y is the cyclic subgroup containing all the powers of S, this is simply the identity in S, then those here are simply all the products of elements of X with elements of Y. All right? In German this is called Komplexprodukt. I'm not sure if complex product is correct in English. It sounds wrong somehow. But this is simply this definition here. Okay, and using this we can deduce what the order of Dn is as follows. First of all, again, see problem set number 9. You convince yourself that the intersection of those two here is simply the identity. Now you assume that you have an element in this intersection, then it has to be of the form R to the K and of the form S to the L, or simply the identity or S. And then, for example, by looking at the actions of those elements on the number on the vertex 1, you see that those are different except when they are the identity. This is a short outline for this proof. Then using this, it is not so hard to show that here this R to the K times S to the L is already the unique representation of the elements in this product here. And finally, after we have established uniqueness, it is easy to see that this map here from the Cartesian product or direct product of X and Y to this complex composite, to this product XY, doing simply the following, taking those elements of these cyclic groups and combining them in Sn is actually bijective, meaning a one-to-one correspondence between this set and this here. And this simply follows from uniqueness because, and K and L, forgot to say always as defined above, here. Uniqueness guarantees that there are no different tuples R to the K, S to the L, and R to the K prime, S to the L prime, such that their product would be the same element, because this would violate the uniqueness here. So this clearly is a bijective map. And then if I have a bijective map between two sets, they are of the same order. They have the same number of elements, because bijective means a one-to-one correspondence. So the order of Dn is the order of this here by definition, or by what we found out here. And now, because of this bijection, this is the same as the order of this Cartesian product, which is nothing but the product of the orders of the two factors. Because here, if I have 4 elements here and 2 here, clearly this product contains 4 times 2 tuples, so 8 tuples. So this is this. But then the order of this cyclic subgroup is n, because this is the order of this n cycle. And this here has order 2, so I end up with order 2n as we expected, because we already know or discussed the dihedral group in another context using matrices. Okay, now if we take all of these facts together, we arrive at proposition 12. If I have any natural number greater than or equal to 3, I can find two permutations R and S in the symmetric group of degree n, with the order of R being n and the order of S being 2, such that they satisfy this commutation relation for all the k's listed here. Yeah, we already wrote down the R and S explicitly, so they clearly exist. Then we saw that the subgroup generated by them, this here, can be written like that. All the elements look like that. This clearly is a subgroup of Sn and is called the dihedral group of degree n and corresponds to the symmetry group of the regular n-gon, because this is how we constructed R and S. And it is a non-commutative group for those n, and we just showed that its order is 2n. And this concludes our matrix-free discussion of the dihedral group. And it's very important to remember this here and this, because dihedral groups are often used as examples or counterexamples or to illustrate new propositions or theorems. All right, as always, please take a close look at problem set number 9. Try to do as many exercises as you can on your own. And it's again a bit on the longer side, so maybe we'll stretch it out over 2 weeks. I don't know yet. Let's see. All right, thanks for watching and hope to see you soon. Bye-bye. Oh, sorry, it's me again. Let me give you a quick outlook with a very interesting example. If you know about linear algebra, you know that this is a very easy theory compared to group theory, because we have very much axioms for a vector space, we have the nice linear structure, we have commutativity. And if you take two linearly independent vectors in a vector space and look at the span of those vectors, this corresponds to the subgroup generated by two elements. This in the linear algebra, in linear algebraic terms, is the span, the smallest subspace that contains these vectors. This is always k to the 2, so very easy. There's nothing mysterious going on here. Whereas in group theory, we have, for example, this here. This is a nice example taken from Dummett and Foote. You take a group where you have two elements, u and v, that satisfy the following. U to the 4th power equals v to the 3rd power equals the identity. And the following commutation relation, uv is the same as v squared u squared. Well, at first look, you might think, whoa, maybe this here has order 4, this has order 3, so the smallest subgroup of those should maybe be the product, the complex product of the two cyclic subgroups consisting of those elements here, and should maybe have order 12. 4 times 3 is 12. Well, this is completely untrue. This whole set here collapses to simply the identity. If you use these relations and a little gymnastics, then you find out that only the identity can fulfill this here. So take this as a word of caution. Group theory is much, much harder than, for example, linear algebra, and things that look seemingly clear or easy can be very difficult or somewhat counterintuitive. All right, now that's it from me for this week. See you in the solution videos. Bye-bye.